Ready. So today we're in 3.7, and this is the first day. And we're going to look at y equals cosine of x squared plus x. Okay, so like we usually do, we're going to take the derivative of this. So I'm going to put a big d dx around it. And that symbol means take the derivative. Okay, so when you take the derivative of x, that's 1. So let's do that first down here. That's probably the easiest part of it. Derivative of x is 1 as well. Okay, this is a chain rule because it's cosine of x sitting inside a squared. So when you take the derivative of x squared, that's 2x. So that's 2 times blank. Need some more space here. So that was the first step of the chain rule. Take the derivative of the outside. Then you plug the regular inside into it. And then to finish the chain rule, you multiply by the derivative of the inside. So there's the chain rule for that. And then, of course, the derivative of y is y prime. Okay, so nothing new there. Let's say that was part A of example 1. So here's part B of example 1. Okay, and this is the new topic for today. So what's different about this equation as opposed to this equation? The difference is this one's not solved for y. So it doesn't have y by itself. Well, it does have y by itself, but the problem is y squared is over here. So it's not just y with a formula that has x in it. So it's not solved for y. So that's the topic today. We're learning how to take the derivative of something that has y's in it. And that's called implicit differentiation. So implicit differentiation is taking the derivative of something that is not solved for y. So we're just going to try and proceed here and take the derivative straight up. Okay, so derivative of x is still 1. That's not a problem. And when you look at y squared, it's tempting to write down the derivative as 2y. But this is actually a chain rule here. And the reason why it's a chain rule is, if we did solve this mess for y, there would be some equation in there instead of y. Just like over here, there's a cosine of x that's being squared. I don't think y is cosine of x over here, but maybe it is cosine of x being squared. So whatever y equals, that formula is inside that y there. So because of that, I call this a disguised chain rule. It doesn't really look like chain rule when you just look at y squared, but since it's y squared, it is a chain rule. So you take the derivative of the y squared just like normal, that's 2y. But then to finish out the chain rule, you have to multiply by the derivative of the inside. And the inside function is y, just like over here, the inside function is cosine of x, because that's being squared. So here the inside function is y, and the derivative of y is called y prime. Or if you watch the video, he called it dy dx. That's the same thing. Okay, so is everybody okay with where this y prime came from. It's the main topic of today. Okay, and then over here, you can even kind of treat this as a chain rule. If this was just an x, the derivative would be 1. So the derivative of y is just 1. But then you have to times by y prime from the chain rule. Or, I mean, the derivative of y, we've been writing that down as y prime for a while. Okay, so now you have to solve that for y prime. So you move this stuff over here. So you have y prime minus 2y, y prime equals 1. So I just subtracted that over. And then you factor out the y prime. So after this step, I'm just doing algebra to get y prime by itself. And then you divide the 1 minus 2y to the other side. So it's 1 divided by 1 minus 2y. Okay, so the new thing today is we've got this equation that's not solved for y, and we're just taking the derivative of it the way it is, and that's called implicit differentiation. All right, so example 2 is y equals the sine of y plus y cubed plus y plus 5x. So we're just going to take the derivative of everything. So put big parentheses around it and say, I'm going to take the derivative. The derivative of y is y prime. The derivative of sine of something is cosine of the something. So the outside function is sine. So cosine is the derivative of the outside function. Then you plug the regular inside into it, which is y. And then you multiply by the derivative of the inside. So even though this doesn't look like chain rule, it is, because we've got a big mess, whatever y equals. So I'm saying if we solved this for y, y would equal a bunch of stuff. And that stuff is sitting there. So that's why this is a chain rule. But it's a disguised chain rule because y looks pretty innocent, like x does. But y is not innocent. It has a bunch of stuff inside of it. So that's where that's coming from. Everybody still okay with that? Yeah. So if I rearrange this whole thing and solved it for, and it wouldn't solve to be this, but let's say it did, then the derivative of this wouldn't be 1. It would be all of that. So that's why I'm putting that there. Whatever the derivative is, we don't know what it is, but whatever it is, we'd have to times by that to finish out the chain rule. Totally good? Okay, so then here, this is another disguised chain rule because it's y cubed. So you do the derivative like normal, 3y squared, but then you have to times by the derivative of the inside. So the derivative of y cubed is 3y squared times y prime. And then the derivative of y, if it was just x, it would be 1. But it's not just x, it's a chain rule, and so you have to do 1 times y prime. Now right here, the difference between this one and this one usually throws people off. So the regular derivative of x cubed is 3x squared. So the regular derivative of y cubed is going to be 3y squared, and then times the y prime. If this was an x, the derivative would be 1. So since it's a y, the derivative is 1 times y prime. And after a while, maybe you won't even write that 1. And because of that, it confuses people, because people wonder, well, this has something with it, but this doesn't. So if that's going to bother you, it's okay to put the 1 there. We could have put that over here, too. This is 1 times y prime. Everybody still doing okay? All right, and then the derivative of 5x is 5. Because that's not a disguised chain rule, because it just has an x in it. Okay, so at this step here, we're done with the calculus, but we want to figure out what y prime is, so we need to solve for y prime. So all the stuff that has a y prime in it, we need to subtract it to the other side. So y prime minus the cosine y times y prime minus the 3y squared times the y prime minus the 1 times y prime equals 5. So I'm just doing algebra to try to get y prime by itself. So I moved everything that had a y prime in it to the left. And then I left everything that didn't on the right side. This time there was only one thing that didn't. There could be more stuff that doesn't have a y prime with it. So then once you get all the y primes on the left side, you factor out the y prime. So it's y prime times 1 minus cosine y minus 3y squared minus 1. So I just pulled out the y prime because that was multiplied by everything over there. And then this 1 minus 1 it combines to be 0. And then I can divide that over. So final answer is y prime equals 5 divided by negative cosine minus 3y squared. All right, how about x squared times y minus x times y squared equals 4? And I haven't been writing directions, but what we're doing is we're finding the derivative. It's called dy dx. Okay, so since we're finding the derivative, what we need to do is we need to put parentheses around this and take the derivative of it. So write d dx in front of it, and that means take the derivative. There is a subtle difference between those symbols and these symbols. This is the derivative. This is a noun. It's the answer. And then this is a verb. This says take the derivative. So when it doesn't have the y on top, it's just saying do it, take the derivative. And then this is the final answer. All right, so when I take the derivative here, it's a little bit different because this is a multiplication, so that's a product rule. So when I take the derivative of this part, product rule is going to be necessary. So I take the derivative of the first thing times the regular second thing and then plus the derivative of the second thing times the regular first thing. So all of this is just the derivative of this first product. Is everybody okay with that? So this problem is harder because we were doing disguised chain rule in the first couple examples, and now we're throwing in disguised chain rule with product rule. So I'm doing product rule, but within that there's a chain rule because there's a y. Same thing here. This is two things multiplied, so I have to do product rule there. So it's minus the derivative of the first thing, which is just 1, times the regular second thing, plus derivative of the second thing. And the derivative of the second thing is going to be tricky because it's y squared. So it's disguised chain rule. So the regular derivative is 2y, and then the inside is y. So it's going to be times by y prime. So derivative of the second thing is 2y y prime. And then times regular first thing. Yes, sir?
Can you explain again why you have x squared is not a disguised but y squared is not disguised?
It comes from the fact that x is the input variable. So when you graph, x is on the bottom and y is here. And so since it's the independent variable, that means you start with it. It's just a number. Whereas y is obtained from a big formula. So since x is the independent variable, it doesn't have a formula associated with it. Whereas since y is the output, it's coming from a big formula of x. And so even though it doesn't look like there's a formula there, there is. Because usually we have y equals this big mess. And then so that's the main reason, but more subtly, when we write d dx, that means that x is not a formula. X is the variable. And then everything else is a formula. So this d dx signals here that x is the main variable, it's the independent variable, and therefore it's not a disguised chain rule. Good. Yeah?
So is that equation, like that was given at the beginning of the example, is that going to be used to find y equals later, or is that a separate formula?
Well, the problem is it's very hard to solve this for y. And so that's why it's not given in y equals form. So some equations are easier to work with, not in y equals form. And so we'd rather not solve it for y. But yes, theoretically it could be solved for y, maybe. But we're just deciding to work with it from this stage so that we don't have to bother with that. And the purpose behind implicit differentiation is to be able to get the derivative without ever solving it for y. So you might remember on Friday we had that x squared plus y squared equals 25 formula. Since we hadn't learned this, my intent was for people to solve it for y and then take the derivative. And that was a pain to do it that way. But it would have been easier using this method. So that's the purpose of this method. Good. Yeah, and it bothers people because we're so used to having equations solved for y that we don't work very much with them not solved for y. Okay, so is everybody okay with this being the derivative of that? Okay, and then this will throw you off. What's the derivative of 4? 0. The limit of 4 is 4, right? But the derivative of 4 is 0. So just watch out for that. When you take the derivative, put a 0 here. At some point, you might accidentally put a 4 there because you're thinking about all the hard stuff. Just watch out for that. Okay, so now I need to move all the stuff that doesn't have y prime over to the right. So that's this one and this one. And I'm going to leave the y prime x squared minus the 2y y prime x on the left. So that term and this term are staying on the left because they do have y prime. And then the two that have arrows under them are going to be subtracted to the other side because they don't have y prime. I said subtracted, but this one's negative, right? So I need to add it to the other side. So at this point, the calculus was finished, but we're trying to get y prime by itself because the direction said find the derivative. So we're looking for a formula for the derivative. So all the stuff that had y prime is on the left. All the stuff that doesn't have y prime is on the right. So now I can factor out the y prime. And then I can divide to get y prime by itself. So final answer is y prime equals negative 2x y plus y squared divided by x squared minus 2yx. Okay, so let's look at this one. This one's like the one on your cow from last week. So I got x squared plus y squared equals 9. And we're going to find the slope of the curve at x equals 0. So if I want the slope of the curve, that means I need the derivative, right? Because the derivative is the formula that gives me the slope of the curve. So I need to take the derivative of this. And this one, it's possible to solve it for y. So that's what happened in Friday's cow, is it was possible to solve this for y. So that was my intent, that you would solve it for y and then take the derivative. But today we now know that you don't have to do that. You can just leave it the way it is and take the derivative from that stage. And that's called implicit differentiation. Sometimes you have a choice. Like in this problem, it's possible to solve it for y, so you could do that and then do the derivative. But there's other problems where it's not possible, so that's why implicit differentiation exists. Okay, so the derivative of x squared is 2x. And then the derivative of y squared is a disguised chain rule. It's 2y times y prime. And the derivative of 9 is 0. So then you subtract the 2x to the other side. And divide the 2y to the other side. And then the 2's cancel, and you get negative x over y. Okay, so now we have the formula for the derivative, which is what the first three problems were asking for. But this one's asking us to go a little further. It wants the derivative at a certain number. So now we need to plug x equals 0 into that. So that's going to be y prime equals the opposite of 0 divided by y. So how are we going to figure out what to plug in for y? Yeah.
Plug 0 in.
Yeah, the original formula gives you the x's and y's that are on the curve, right? So if I put a 0 for x there, then I can figure out what the y should be. So when that happens, you actually get two different y's. You get both positive and negative 3. But it doesn't matter, because either way, this is going to divide out to be 0, right? Now, why did I even bother solving for y? Didn't I know 0 divided by anything was going to be 0? There's one number that, yeah, it could have been 0, in which case it would have been does not exist. So I had to be a little bit careful. But 0 divided by most things is 0, but 0 divided by 0 isn't 0. So I had to watch out for that. Plus, I wanted you to realize that you could find the y value by using the original formula. Okay, how about this original formula? Does anybody know what kind of a graph that is? It's a circle, and the center is 0, 0, because nothing's being subtracted from x, and nothing's being subtracted from y. Like if it said x minus 3 squared, then the center would be 3 comma something. But since it says x minus nothing, it's 0, 0. So the center of this circle is 0, 0, and the radius is 3, because that's the square root of 9. So if you graph this, it would have center 0, 0, and radius 3. So I know it goes out to here, and up to there, and out to there. So there's what the circle looks like. And then we were trying to find the slope when x is 0. So there are two places where x is 0. That's there and there. That's the 0, 3 and the 0, negative 3 that we found. And it's true that the slope is 0 at both of those locations. So this is just graphing to show that this is the correct answer for the slope of this curve at 0. Okay, so again, the purpose of implicit differentiation is you don't want to bother, or you can't solve the equation for y. So you just take the derivative in the form that it's in, straight up, which is easier because then you don't have to rearrange stuff. But it's a little bit trickier because then disguised chain rule happens. And you can accidentally, since it's disguised, you can overlook it and not do the disguised chain rule.